We are Group 7, and our project is simulating riser unloading events using computational fluid dynamics software. My name is Brian McCanley.
I'm Garrett Ruiz.
I'm Parker Jones.
And I'm Ross Teichman.
And our advisors are Dr. Akbari and Dr. Tiagi.
So a little bit of background about our project first. A marine drilling riser is a series of conduits that connects a subsea BOP to a floating drilling vessel. Now, the riser has a large diameter main tube with external auxiliary lines that include high pressure choke and kill lines for circulating fluids to the subsea BOP. The riser is kept in place by way of a marine riser tensioner, which is located on the drilling platform. The marine riser tensioner acts to maintain a near constant tension force large enough to ensure the stability of the riser in the offshore environment. So one of the biggest problems of drilling anywhere is that gas kicks can be dissolved into oil-based mud, which leads to it being very difficult to detect these kicks. So our project aims to gain insight into methods of predicting and preventing gas unloading events above the subsurface BOP. But how will we accomplish this?
To accomplish this, we will be simulating industry conditions using CFD software. The focus of our project will be studying free gas in the riser. Gas kicks are of significant consideration because once gas is in the wellbore, it often goes into solution with the drilling fluid and there's no observable sign that the gas exists. As the gas rises, pressure is reduced and gas eventually comes out of solution. Tendency for gas to break out later in the wellbore can leave the crew with little time to react to prevent the kick from reaching the wellhead. We will use ANSYS 3D modeling to construct our riser, and we will use a VBA package to generate vertical flow parameters in the riser. After these have been constructed, the CFD material will populate the 3D mesh with fluids.
So when we're running these simulations, some of the parameters that we're going to be able to control and manipulate are the circulating pressures, the bottom riser pressures, the circulating speeds, the mud gas concentrations, and the actual riser design itself. And then what we're going to be getting out of this is actual data that represents a realistic riser unloading event.
So by manipulating these input parameters, we were able to create several sets of data that represent several different situations in which gas can enter the riser, be circulated, and then unloaded onto the rig floor. We can analyze these data sets output by our simulations for pressure behavior and mud gas concentrations throughout the volume of the riser.
Now, one of the biggest advantages that we have running these simulations as opposed to studying this in the industry is the fact that with CFD, we can have the pressure at any point in our riser as opposed to just at the surface or at the BOP. So our end goal is to determine whether there are any signatures or warning signs of an impending riser unloading event.
Uncontrolled gas in the riser that reaches the wellhead can result in major health and safety concerns. Once gas is exposed to the atmosphere, there is a good chance of ignition which can result in loss of life as well as damage to equipment and facilities. Situations where extreme blowouts occur, such as the infamous Deepwater Horizon, can cause extreme pollution to surrounding marine ecosystems. Deepwater Horizon's cleanup involved over 30,000 responders to reverse the harm done to the Gulf of Mexico.
So to run these simulations, we'll be using ANSYS Fluid. We worked both with each other and with the mechanical engineering department to gain access to these CFD-enabled labs. We also attended several CFD tutorial sessions. At these sessions, we learned the basics of modeling 2D internal laminar flow. We were then able to modify the mesh that we created in the tutorial session to create an annular flow geometry, which is what we're going to be focusing on in our simulations. You can see here in these graphs, these are a couple of examples of what we output with our simulations in the tutorial sessions. They display the velocity profiles of the laminar flow that we simulated. We're going to be able to generate similar graphs with our simulations that will be able to show the pressure profile throughout the riser.
So, beginning with the tasks and goals that we have moving forward. First, we need to master the CFD software syntax to be comfortable with the program. Then, we need to familiarize ourselves with the new VBA applications, specifically that of a program that Dr. Tiagi has provided us that calculates the vertical flow parameters that we can use for our riser. Then we need to solidify our knowledge of our numerical method used to run our CFD simulations and determine the set of input parameters.
So based on those tasks and goals, we went ahead and delegated some roles and responsibilities. For the riser specifications, the 3D mesh, and operation of VBA software, we decided to assign at least 2 people to each respective topic. We did this to ensure that no one person felt isolated and became stuck on any particular aspect of the topic. We feel that it's important to have at least one person to bounce ideas off of and work through any issues that might arise. And for these last 2, the numerical simulation and the operation of the actual CFD software, everyone is responsible for learning this material because they are the most foreign subjects to us and, in essence, are the core of this project. For our budget, really the only economic factor that we had to deal with was acquiring a license for the Anson Fluids software. And as we previously mentioned, we were able to gain access through the mechanical engineering department. This was very fortunate for us because purchasing any CFD software license of this caliber would have costed thousands of dollars to purchase. Not to mention, finding a computer with the actual processing power required to run this software is very difficult because most of our laptops do not fit those specifications. Also, there are many tutorials online for free, so learning to actually operate the CFD software will not incur any additional costs, so that's nice.
So as far as our, oh, sorry, go ahead.
Yeah, for the time frame, by the end of the semester, we're hoping to actually solidify which marine riser design specifications we're going to go ahead and use. And for by the midpoint of next semester, we're hoping to have mastered the actual CFD software and the respective syntax, and also have completed the 3D mesh of the riser design. And by the end of the academic year, we're hoping to have developed and fully run these simulations. That way we can do the data analysis that follows.
So, as far as our resources go, here are some of the things that we're going to be accessing throughout the remainder of our project. Dr. Tiagi will mainly be helping us with the CFD software and the operation of that. There are going to be some code additions that we're going to need to throw in there that will be adding the two-phase flow aspect of our simulations, which is not included in the CFD software at this moment. Dr. Akbari will be helping us mostly with the data analysis side of our project, where we'll be looking for those pressure patterns that may suggest a kick being in the riser. We currently have a set of riser specifications from National Oil Well Varco, but we're going to be seeking additional information confirming that that is going to meet the industry norms in order to ensure that we have the most applicable data possible. Finally, there's a textbook provided to us by Dr. Tiagi that outlines the finite differential method. That is going to be the method that we're going to be using to perform our simulations. Thank you very much. If you had any trouble seeing any of the slides, there's a link to our PowerPoint in the description below. Other than that, have a great winter break.